Welcome to our next session, Experts Insight Short Presentations. These Experts Insight have been prepared with VDMA Working Group Additive Manufacturing, and I'm very happy to have three experts here on stage which will show new technologies for new applications. Our experts are Maximilian Dropmann, he's Development Engineer Additive Manufacturing at GROB-WERKE. Tobias Stittgen, Managing Director of ponticon. Sonja Baumgartner, Head of Business Development of Cubicure. And I think we start right away into our presentations. So, Maximilian, the stage is yours.
Yeah, thank you for introducing me, and thanks for giving us the opportunity to introduce you to our new, unique technology. The GROB-WERKE Mindelheim is usually not known for AM technologies. We have around about 8,000 employees worldwide. Most of them are doing something different. Some of the applications you can see here. But there's a small group of engineers that developed a new and unique AM technology since 2018. And this technology is called liquid metal printing. So let me tell you what it's all about. Here you can see our first series machine, the GMP 300. It's the first machine that has such a high level of automatization, so you can use it in an industrial environment. Let me explain you how the process works. We have a crucible that is heated, and we feed a wire into the crucible. So the wire melts, and there's a little bath of liquid material, and in this bath there's a piston. This piston is moving vertically, so this movement generates a little droplet that's dropping out of a nozzle at the bottom of the crucible. So this little droplet falls on a build plate, and we move that build plate horizontally so we can build up different parts with different elements and so on. There are overlapping elements possible, so when you have an angle 30 degrees off the vertical, it's possible to print without supporting structures. If that angle is higher, you need supporting structures. The advantages of the process are, first of all, we use a wire as raw material, so we don't have any problems with other materials considering health risks, need for ventilation, for example, when you use powder or some exhausting system and so on, no explosion risk. And we have less post-processing work to do, so no sieving and preparation of powder, for example. And the wire is not as expensive as other materials to buy. Then we always say our process is not a welding similar process, but more a casting similar process. We call it micro casting or incremental casting. There's low thermal distortion because we can control the temperature on a pretty low level. Maximum temperature is around about 30 degrees above the solidus temperature, and we can achieve a homogeneous microstructure. Some mechanical properties of the printed parts are even higher in the final state than it is in the raw material. For example, strain rates and so on. Then we have a high flexibility and high productivity. We can change the material real quick, as you maybe saw in the video. We can also vary the droplet diameter. So there's some strategies you can choose. You can use a small droplet diameter. You have more production time, but you can have smoother surfaces and more precise parts in the end, or you can say you need the part real quick. You take a big droplet, a high frequency. The surface gets rougher, but you have the part in your hands in a very short time. High productivity, we have high build rates. There's a calculated value. We say it's 320 cubic centimeters per hour. We have less post-processing, as I said. Yeah, we have no scaling of the component costs via the filling level. Here you can see some of our applications with different functions. On the left top picture, you can see an application that is supported from the bottom. We have them all shown at our booth C51. You can have a look, and you can even touch them and see the difference between a high droplet, a big droplet, and a small droplet, and so on. We are happy if you visit us. Maybe you have some application in mind. We can discuss how to make it printable on our machine, and we can have a chat and so on. So here's my last slide. It's the machine data. Just to highlight some of it, we have a build space 300 on 300 on 300 millimeters. We have a maximum drop frequency of 500 hertz. And we have different diagnostic systems, camera systems, to control the process and to adopt the process if it's needed. So thank you. That's it for now.
Yeah, thank you very much, Maximilian. I have the one or the other question concerning your new product. It's very impressive because yesterday or the day before, I'm not sure about, I said we must bring more of the, let's say, old or the traditional machine experts and machine vendors to Formnext, and now you are here, so somebody heard my wishful thinking.
Yes.
Yeah, I visited GROB at AMB, so you're a very classical machinery company, but I wonder, do you compare, or how do you compare the new technology with your traditional technology? Do you plan to combine it in a hybrid machine? Because this is just an additive machine, which is, I think, which is very fine. But you're very well in the subtractive area as well. So, is it a new step, and you will abandon the subtractive, or do you want to combine it? What is the strategy behind?
No, there's an idea in the pocket to combine it, because as you know and as you can imagine, there's a drop-based building of parts, so the surface is not very flat. So, but it's like with all the other technologies, if there's a demand that there's a contact to another part, or you want to
functional surfaces, yes, something like
and
that,
so on. You always need to machine it in the end.
But may I interrupt you? What is the droplet size? What is the finest surface you can achieve?
The finest surface is like the minimum droplet that's possible right now is 270 microns. So this shape is, you can always see it at the surface of those parts. So in the end, when you use a very small droplet in this size, there's a surface quality of RA 20 microns, round about that. So it's quite smooth, but in the end, if there's some functional areas, then you machine it. And then there's this idea in the pocket to combine the two technologies. Like, it's a perfect match at GROB, but to combine it in one machine.
But in future you will have both. You will have just a machine for 3D printing, maybe one day a hybrid machine, yeah, and the traditional subtractive ones.
Course.
That's a picture.
Yeah.
which materials can you process? So are there the standard steel materials, or which? What is the coverage here?
In the first step, we decided to develop a machine with a maximum temperature of 1,000 degrees. So we can print the whole aluminum alloys. We started in the first step with a 4047, so ALSE12, which has quite high process times. We kind of developed step by step other alloy materials, for example, copper, magnesia, zinc, mangan, and so on. There's always some special things you need to respect, and we're developing it right now. Yes, and so we have a larger field of elements that we can print. Looking in the future, we already have a cooperation with a university concerning printing copper. We also had the first tests on a prototype, which were quite good, actually. And of course, when you look in the far future, maybe there's steel in some time.
So that's a range of materials you were not so busy with in the past. I think it's
yes.
You're gaining a new field of materials as well in your company.
Yes.
Okay, perfect. One last question for now. We can have a chat after the three presentations. What does the machine cost? Can I buy it today?
Yeah.
I have some
the machine costs 590,000 euros, but there's a...
I have to ask my wife.
Would be better. Yeah. There's a exhibition price with 450,000 euros. It's limited for the duration of the exhibition.
Okay. The audience, ask your financier if there is some spare money left. Thank you very much for now.
Thank you.
I'm happy to have Tobias Stittgen here. He's managing director of ponticon, and I'm very curious what you brought with you.
Yes, thank you very much for having me. Let me just grab that part really quick. So at ponticon, we've developed a technology that we refer to as dynamic material deposition. Essentially, it's a DED process, so we're feeding metal powder through a nozzle, which we then melt by means of laser radiation. The trick that we're doing here is that we're relying on a processing principle where we melt the powder while it's still in flight. I think it's nicely shown on the image on the left-hand side. So the powder interacts with the laser beam while it's still approaching the part that we are either 3D printing or coating, and then arrives on the substrate in an already molten state. And this processing principle allows for very high feed rates. So it enables movement speeds of up to 500 meters per minute from a process perspective. And now, obviously, this is something which you also have to resolve on a mechanical engineering level. And that's where ponticon comes into play. So we have developed a highly precise, highly dynamic, parallel kinematic system. The machine is showcased in Hall 12.0. It's 11 tons of weight. So this image doesn't really represent how impressive and tall it is. There's 7 tons of granite to the frame, which you need for precision and to compensate the very high forces. We will have a look at some videos in a second. And so as a result, you get a manufacturing technology that is highly productive, highly precise, and at the same time very flexible in terms of combining different materials. This is a result of using the nozzle for feeding powder, so you can do any kind of combination. You can change the alloy composition in real time, and this is a really handy feature, especially when talking about materials for AM, where we believe there's a lot of opportunity and potential in the future. This is the technical background. Let's have a look at how the system works and how it looks like in reality. That this video starts. So I have to mention, this is real time, what you're seeing now. It's 50 meters per minute feed rate right now, and then we're accelerating. In the background, you can see one of the linear drives doing an up and down movement, which is then translated into X, Y, Z by 6 connecting rods. So there are 3 drives on the machine, 3 degrees of freedom, and then you can realize high speed, high precision, X, Y, Z movements. So now we're getting close to the 200 meters per minute. In this setup, the optical system, the processing head is stationary, which is not a very typical approach, but it really helps to get to the high speeds and have the high dynamics. You can see a turn-tilt axis on the bottom of the machine, so if we have more complex parts to additively manufacture or to coat, we can change the setup within 2 minutes and then do processing of more complex geometries. So what we just saw is the technology, and then again, high-tech is essentially pointless if you have no applications. So that's what it's all about, and I just mentioned it. We're looking into coatings, and we're looking into additive manufacturing. On the coating side, this is how it looks like. Again, real-time, 30 meters per minute feed rate. I will slow it down in a second so that you get a better feeling of what's going on. You can nicely see the optics in the stationary setup, feeding the metal powder, and then we switch on and off the laser at a very high frequency to only deposit the material in the area where we actually want to create a part. So let's slow it down a bit by a factor of 8 in this case, so you can see the laser just doing a very short pulse for a few milliseconds in this case, then doing the big part in the middle. So there's a lot of know-how in controlling the laser, making sure that you switch it on at the right point in time, that you really hit the areas of the workpiece that you want to hit. Especially in coatings, doing multi-materials is a very relevant thing. So you can do functionally graded materials, you can have a very ductile connection to a part when you do a coating, and then the further you get to the outside, you can include tungsten carbides, carbide particles to increase the hardness. So when we talk about wear and corrosion-resistant coatings, this is a very handy feature of working with nozzles and feeding metal powders through them. On the additive side, and again, I think this is a very nice showcase for the technology because you can actually see the part growing in real time. So we do this circular or elliptic movement. In this case, feed powder mass flow approximately 8 grams per minute. And so this is a nice example of precision and productivity. So this is an aluminum part, 500 micron wall thickness, and print time for this entire thing is just 40 minutes. If you would do it in powder bed fusion, it would take at least 10 hours, and the surface finish is really comparable, if not better. So there was no post-processing carried out on this. And so we can do a lot of work in the additive manufacturing domain as well. Aerospace applications, automotive, robotics, renewable energies. So with this material flexibility, the very high precision and very high productivity, we can enable applications for the first time that industrial end users haven't been capable of leveraging up to now. Hoping that I didn't exceed the 5 minutes too much.
Fine.
I'd like to thank you for your attention.
That was very impressive. Thank you for bringing us the nice video material to get a better idea. May I lay a hand on your piece?
Absolutely. And sorry for the wrong last slide. It still has the dates of the last conference. Just really.
No problem. The audience, that really looks impressive because it's a very smooth surface. And it's just, you do not see so much, structures of the processing size. But it's a rough structure or a rough surface as well. So what is the minimum particle size you can, or the minimum
layer height?
Yeah.
So this is done with 100 micron layer thickness. Smallest we can do is 30 microns. at the end of the day, it depends on the powder you're working with, and we like to work with powders from 15 to 45, and then also bigger fractions. So that would ultimately define how thin the layer could get.
Our session has a title that in the title, the application part. So which new applications do you see coming along with your machine?
Yeah. I think rocket propulsion is a very relevant example. So thrust chambers, where you have two major requirements, heat conductivity and then a lot of mechanical strength. So here you need to combine materials, for example, copper-based alloys, nickel-based alloys. And here this capability of transitioning from material A to material B comes in really handy, because you can realize the high heat conductivity on the inside, can go for complex shapes, and then for the mechanical integrity and strength, you would coat what you just 3D printed with a nickel-based alloy, and then do the entire thing in one technology.
Can you give us an idea how long did it take to engineer such a machine? How many years? I don't know.
So we installed our pilot system at Fraunhofer ILT in Aachen in 2019. And back then we did a lot of engineering work, making sure that you could not feel buildings 100 meters away shake because of the very fast movements. All of this is resolved, and now it's more about the software side and getting most out of the mechanical stuff. So the kinematic system and everything is really doing what it's supposed to do. And now it's about enabling the applications on the software side, CAM environment, and those kind of things.
How many of these machines or plants?
Yeah.
It's a bit more than a machine, I think. Did you already sold?
So we're showcasing system number 4, which we will install at Karlsruhe Institute for Technology in January. So as of today, we have a very strong footprint in academia, and at the same time carry out feasibility studies for industrial end customers. So I expect the first orders from industry by the end of next year.
And would you share the price as well?
Yeah, of course. So with the laser powder feeder, you need some periphery. It's somewhere in between 1.2, 1.7 million euros.
So nothing for me at home as well. Thank you very much.
Thank you.
And we are coming to our third presentation in our session. Sonja Baumgartner, Head of Business Development of Cubicure. Sonja.
Hello.
What have you brought with you?
So thank you for having me here today. I have something different. So I'm talking about polymers today. So as we've seen in the last days, additive manufacturing seems to have overcome most of the traditional issues it had in the last years, so surface roughness and mechanical properties, and also there are a lot of technologies available who try to scale up the processes. But every time you ask industrial customers what they actually need or why do they not yet use additive manufacturing as real production technology, then you always end up with the same 3 things. And the first thing is they want a scalable process, so they really want to use it. So if they want to use it for serious production, it has to be a scalable process. So they don't want to use 100 printers to print 1 part each, but they want to print 100 parts on 1 machine at once. And the second thing is specific material properties. So certain mechanical properties, or like in the conductor industry, so the specific application I'm talking about, for example, flame retardancy or dielectric properties. But the third thing is, and this is one of the most important things right now, is a reliable post-processing solution. Because if you want to go into serious production, you don't want to manually handle thousands or even millions of parts. So this is what we are actually looking at. So what is Cubicure doing? We developed a technology we call Hot Litography. So what is Hot Litography? We're using DLP and SLA-based printers, but we're heating them up. So if you want mechanical properties which are good enough for industrial products, you end up with resins which are very hard to process. So our resins are very high viscous, and you cannot process them with any other SLA or DLP printer around. So we had to invent a new process how to actually process those difficult materials, as I call them. So last year, we, for the first time, presented a scaled-up process for these high-viscous materials. It's our Cerion system. You can actually a little bit see it on the left picture there. The build platform is very large. It's 1 meter times 300, 300. So you can actually have either one very large part or a lot of small parts. The problem with scaling up DLP and SLA processes was always that you either have a large bath with hundreds of liters of resin, so you need a lot of resin and you can more or less throw it away after a few prints, or you have large platforms, but the platform size are always limited because of the separation forces. So every time you try to lift a platform out of a liquid bath, you have high separation forces, and that limits your size of the platform. So we developed a new technology. You can actually see it upstairs if you want to, where we have a carrier film. This carrier film is coated with resin, with a very thin film of resin, and it just lays down the resin, and while moving over the platform, it's getting cured. So it's more or less a scrolling image, and so layer by layer, it's cured. And so if you want, you can go down to 10 microns of layer thickness, but then it takes forever. So usually we print between 50 and 100 microns layer thickness. And the resolution of the pixels, so we're using DLP beamers, is 50 microns. So we have very high resolution. We have the good surface quality of DLP printing, and we have very good mechanical properties. And so one of these industries which was calling was the connectors and electronics industry, because they were looking for exactly that. Why? Because the connectors industry, they have small parts, they have very complex parts, and they have small batch sizes. So they typically have batch sizes of 1 up to hundreds of thousands connectors. But so nowadays, most of the connectors are customized, so they really need this flexible production, and they also might want to print several this year and a few thousand next year. So they want to be flexible. And so here on this image, you can see a connector with 96 pins. And so an injection molding tool is so expensive and so difficult to produce. So it actually needs more than 1 year to produce a tool for that. But you can print it within 2 hours. So just to give you an example, so one of these connectors, actually the small one on the upper right picture, you can fit 2,000 on one platform. It's printed in less than 2 hours, so we're down to cycle times of a few seconds, 3 seconds more or less. So we're pretty close to injection molded cycle times already. And we have the material properties and the surface quality of injection molded parts. So we really ended up with a process which is ready for industrial applications. And so about the post-processing, so now we ended up with a lot of parts, with large platforms, and you somehow have to make sure to be able to wash them and clean them afterwards. So on the right side, you can see an image of a cleaned platform. So the large platform can be divided into small segments, so it's easier to handle in the post-processing. And the platforms themselves are then put in a centrifuge. So after the centrifuge is already pretty clean, most of the resin is away. And we can also refurbish this resin. So this resin is collected and it can be put back into the system. And then afterwards, it's put into a cleaning plant, which then cleans and dries the parts, and they come out clean and dry within 10 to 15 minutes. So we ended up having a whole process for industrial applications like the connectors industry. And if you are interested in how this process works, just visit us at our booth upstairs, or in the internet. You can find anything you want to know on our homepage as well. So that's it for now. Thank you.
Yeah, thank you very much, Sonja. Very impressive again. I wonder if you say it's a scalable process, and you are talking a lot of the post-processing as well, not just the process itself. A lot of information we get here on stage is just dealing with a key process, and not so much talking about the processes around. So in your awareness, is the automation a crucial part?
Yes, it is. But so automation, so combining those single steps, is then like the customer's part. So they usually have like in their plans automations. So the customer can decide how to combine these steps. We have to provide all the single steps. We have to provide the material, the printing process, and the post-processing. But what happens in between, if you like put it out manually or if you want to automate it, then that is part of the customers. Usually they have much more experience in that than we do, so it's part of the customer side.
So are you working on that together with some partners then, or do you really say we are out of the game here?
For the automation?
Yeah.
Yeah, we're working together with the customers, and like we can just give them some ideas how to do it.
That was what I mean. That they are not alone.
No, they're not alone. So if they need any help, we're here.
Ideas how to solve the problem.
Yeah.
Because at the end you said you stressed that it's very fastly produced parts. So it's all about time and cost and time is sometimes the same. So that's an important step as well.
Of course, yeah.
Can you, these connectors, the electronics industry, they normally, or more and more, they want to have connectors with different materials inside. Can you process more materials than one in your system?
Not at once. So you can always use only one material at once. But what you can actually do is like pick and place. So this process is, you can stop it at each layer and just put, like, for example, inlets or something in. So we tried it already with some connectors. So
then
if
again,
you can put in metal
automation.
parts and then continue printing. Yeah, that would be a part of the automation.
That would be part of it. So I take it from when I have the layer achieved, then I go to the next machine, put in a different material of an inner layer or something, and then I come back to the original process step.
Yeah.
Okay, that would be possible. What else? I have a quick look at our time. Maybe we come together because I have just come here. I have a question for you three. From your point of view, you know, we have three experts here, not talking about your product itself, but if you look a bit from a bird's eye view, where's the technology journey heading from your point of view? That was a question because I had in mind the next question. The automation, is it crucial for the customers, for all visitors here? The cost or faster processes, or we talked about a bit materials, different materials we can process, or innovative concepts bringing, you know, hybrid products. What is the most crucial point, or did I miss any point? What do you think? Maybe we start with you, Maximilian.
Yes, I think the important thing is automatization. As we could see in his presentation, there were 3 axes moving really quick, and I think most of the people and the customers still have some respect from this technology. So if you make it easy for them to enter the technology with a good automatization, you only have a couple of steps. You don't need months of experience to use a machine or a special know-how. Then it's an easy entrance, and if there is an entrance, then the people start thinking in AM. So, and I think that's the first.
So
lead.
Make it easy for them.
Make it easy
to include in their own manufacturing processes.
Yes, yes.
What's your opinion, Tobias, or your most crucial point you see?
Yeah. So my take would be really the economic side of things. If you cannot create a competitive advantage with your technology for your customer, then the technology will not prevail. So it's nice to have this machine and to have this high-tech product. However, if you don't get into the applications, at the end of the day, it's pointless. So I would really encourage everybody in this entire domain to focus on the applications and get it done, and not put your product in focus, but put your customer's application in focus. And yes, you have to do automation, and you have to have advanced software and everything, and those things need to be developed. but they always should be developed with a focus and commitment to a customer problem.
Sonja?
Yes, so actually from my experiences, the next big thing is reproducibility. So we have to make sure that machine to machine is reproducible, so part quality is good. And so automation is part of the process, because if you can automate all the steps,
then you get the reproductivity.
Yeah, it's easier to have reproducible results. But first we have to make sure that the process does themselves. So the printing process, the digital preparation, the printing process, the cleaning process, the material production is reproducible, and then the next step is automation of the in-between steps, and then you will end up with reproducible part quality. And so I think this is the next step, and automation is part of that. Yeah.
Okay, perfect. Thank you, Sri, for being with us and for sharing your insights and the new product. You have to work on the costs for me, but I think that's a point in your office as well. Yeah, dear ladies and gentlemen, dear audience here in the room and outside at computers, thank you very much for being with us. After a short break, we will have the next highlight starting Discover 3D Printing seminar here, where you can learn some basics of additive manufacturing, and I hope to see you back then here.